Good afternoon, everyone. I am Santosh Pachu Devanirapuya. I currently work as a senior CPU verification engineer for NVIDIA Corporation. Before starting the presentation, I've seen a couple of presentations from previous years, and all the presentations you usually focus on secure software design. You just talk about the AI models, you talk about the software application layers, but no one touches about operating systems or drivers or the firmware or how exactly the hardware is taking care of the security along with the software, right? So that is something I wanted to bridge a gap between the software and the hardware, because you run your AI model, you train it, you deploy it, you want your model to give the inference as expected, but have you ever thought about from the hardware perspective? Because you use GPUs for training your model, right? Have you ever thought from the hardware perspective? So to bridge the gap, we'll walk through the agenda. So it's going to be, we'll first talk about the different stacks that are involved all the way from the AI to the hardware. Let's connect the dots, and then let's go with what are the trust assumptions when it comes to the OS to the driver and driver to the hardware. We'll talk about two major scenarios, which is very important when it comes to the hardware perspective. We'll talk about what is rowhammer. We'll talk about how can you write a secure code in order to ensure rowhammer doesn't happen in a real-time scenario. We'll talk about unified memory failures, so what exactly unified memory is, why unified memory is important these days. We'll talk about the past gaps and how the industries, like major semiconductor industries, have been taking care. What practices do they follow to design a secure hardware? I've also mentioned the two bugs that one from the AMD and one from Tesla, which was found this year. We'll see like what was the bug and how did they fix it. The last would be like why hardware bugs are also security bugs. It's just not the software. We'll also talk about how do you deploy that into your layers, and we'll talk about the cross-layer security testing strategy. Moving on here, so let's focus on the right side, the diagram that you have. So topmost layer, you have your AI model. Let it be, it can be your ResNet 18, it can be your any deep learning model. You have implemented your model using some SDKs. It can be PyTorch, TensorFlow, or JAX. Now, what next? So you have the operating system. Below the operating system, if operating system has to talk to the hardware, it has to have device drivers. Let's say you have your PC and you buy AMD or NVIDIA GPUs. So you connect your GPU to your hardware. So your operating system, which is running on your PC, should know how to talk to the GPU, right? So you'll have to install the device drivers, right? So the operating system always talks to the device drivers, and end of the day, the device drivers talk to the hardware. So that's the complex hardware that I've shown. You have something called CPU, you have GPU, you have unified memory, CPU is talking to GPU, a lot of things going inside the hardware. So in that entire flowchart, you can actually see that when operating system is talking to the device driver, operating system in a lot of cases assumes that, okay, the device driver is going to take care of the security, so probably I need not do that. When it comes to device driver assumes that whoever manufactured this hardware, he's going to take care of the security aspect. So he might not have a lot of checks when you write a device driver code, right? So it's basically saying where does the security trust boundary comes from. So it's usually the operating system to the device driver and device driver to the hardware. We'll walk into what kind of securities are. So just a point which says that like OS to driver, driver to hardware. Most of the DevSecOps pipelines, you usually focus on the use case testing or maybe like the security testing on the software layer, but you never write test cases which can validate the memory level correctness or the driver hardware enforcements. So, okay, let's come to the one major scenario which can happen in the real-time world. It's called rowhammer. It's very simple. Just imagine, you have rows and columns. So every circle that you see there, it's called as a bit cell. So ideally, it can store like a 1 or 0. It's basically a memory structure. So rowhammer is a scenario wherein you are trying to access a row of memory back to back, maybe like millions of for loops. So you're running a for loop, and let's say the iteration is million. So when you try to access same row of memory back to back because of some electrical inference, so the victim rows or the rows which are adjacenting to the aggressor row, it can get corrupted, or maybe like the bits can get flipped from 1 to 0, because end of the day it's all the transistors, it's the capacitors which basically store the charges over there, right? Now just imagine the red color which I've circled is basically the victim row. You are accessing the aggressor row millions of times together, and let's say the red color bit got flipped from 1 to 0. Now just imagine, what if your model weight, the AI model weight, was stored in that red color, right? So the bit got flipped, which means that your model weight value has changed in the memory. So once the model weight has changed it, let it be how much of a perfect your model that you have deployed, you give some input data to it, it cannot give you a correct inference because the model weight has actually got disrupted in the memory, right? So this can happen very much in a real-time scenario. Two causes, I would say, it can happen naturally, the scenario that I explained, and the other thing, it can also happen, let's say the hardware is basically being deployed in maybe some satellite applications wherein it is exposed to high radiations. So the radiations can also cause the bit flips, right? So that can also be a scenario wherein your model weights can get flipped. So now, how do you write a secure code when it comes to a row hammer thing, right, in order to address? So you have a simple for loop. You are writing a for loop for n number of iterations, and let's say you have the size of the buffer is 1,000, right? And you just try to access every data and you try to do an addition. It's a very simple, you're summing up the data. It's a summation of all the buffer items, right? Now, but a secure way of writing is like this. That's from the hardware perspective. I know you might ask, I am a software developer, I'm just writing a high-level code. This is a very simple code. When I write a for loop, why do I have to include delays, right? But end of the day, when your AI code is taken and the compiler basically compiles the code, it adds some delays. What I mean is, so you take the same for loop, but you put some small delays. That's because we are trying to say that since you're accessing all the items back to back, let's add some delays so that the row hammer scenario cannot occur in the hardware, right? So you also have something called as a jitters, you sleep, and then you basically do the summations. So one more example on the top, okay, you're doing a model inference, you're passing your weight, let's say you have stored the weights, you pass your input and you say the model, okay, give me the inference, right? But you did not do any safety checks over there. The best way to write a code, maybe a small checking mechanism would be, first go try to read the weight from the memory, try to do some hashing, try to validate it against, okay, does the hash match with whatever is the expected hash? Only if it matches, then try to go and infer. If it doesn't match, it basically means that your weight got corrupted. Now you try to load the weight from some last known good value, right? So that would be a better way of writing a code wherein you are ensuring that before doing any inference, you are doing the hashing mechanism to ensure that, okay, my model weights are not corrupted. Now, let's talk from the operating system perspective. Job of the operating system is just to schedule a task, as simple as that. So you have a scheduler, run ready task. But a well-known design when you write an operating system would be, before I schedule any task, let me go and see if any row hammer has occurred. In case if any row hammer has occurred, how to retrieve that, right? So here you basically do something like, you scan the rows with unusually high activations, you do some refreshing. So we have something called as TRR, it's called a row refreshing. So you give some delays, you give some time for the charges to come back, and then you basically schedule the task. It's just saying that always try to add security checks at every layer. So the top one was basically on the AI layer, and now we spoke about the operating system. Then something very similar in the driver. And when it comes to the hardware, let's say you just want to write some data to the memory, right? So that's a DRAM write, a very simple function. You give a buffer, you give the length of the buffer, you write a data. Before writing a data, just go and see if there is any, you have a threshold for everything. Like you take care of the error code counters, you take care of the TRR event count, and you do some checkings with respect to that. And if everything is perfect, if it is less than the threshold, then only go and write it to the DRAM, right? So that's a very, a basic if case, but you can just think that it's a very simple if case, but these things, the ECC and the TRR, this plays a very major role when it comes to the hardware aspects. Well, so the second scenario is unified memory coherence or isolation. You just imagine, end of the day in your hardware, you have a CPU, you have a GPU, and this is a unified memory. So you can imagine like, let's just talk about your autonomous driving car. Let's say you have a camera, your camera is capturing the images. So the job of the system is, if at all you have any obstacle in front of you, it has to give you a signal saying that, hey, there's an obstacle in front of my car, right? So the camera is capturing the images like buffers, like back to back. So those buffers are being read by the camera drivers, and those camera drivers feed that input to the CPU, right? Now, at one end, the CPU is taking all the image buffers which is given by the device drivers, and then he is telling the GPU, you have the AI model with you, I am going to give you the buffers, you process, you infer it, and you tell me if it is an actual obstacle or not, right? So at one end, this guy is capturing and he's storing somewhere over here. On the other end, he's trying to read the same thing. He's capturing, he's reading. Now what happens is, when two different agents try to read the data from the same memory, you need to ensure that there is coherency. So it's very similar to, in software language, you can say you have thread A and thread B. Both of them are trying to access the same shared variable. So you implement mutexes, conditional variables, mutex lock, mutex unlock, whatever, right? So from hardware perspective, we call it as coherency. It's just not in software that you do it. Even in hardware, we ensure we have implemented the coherency aspects, right? So isolation is something like, what you can imagine is, there are certain locations in the memory that only CPU should access. We should not let GPU to access. So we are trying to isolate the memory that only one agent has to access from the other agent. So that's with respect to the coherency and the isolation, which is very important. And any hardware you take it in today's world, you will see that these are the two major things which can really, if it's not taken care in the hardware, your data gets corrupted. No matter your AI code is perfect, your software is perfect, the moment you have any failure in the hardware, that's it, right? So yeah, this is just a table showing that AI, what's a risky practice, and what's the failure mode. So maybe I'll just pick one. Let's just talk about the AI code. I just explained that the CPU is capturing the images, right? And the GPU at the same time is reading the same image to do the inference. So what's the best practice to do it? The best practice is to do it, the CPU, let it first capture the image, put it into the memory, let it synchronize, or let it notify the GPU saying that, okay, I read it, now it's the time for you to read it, right? So ensure you have synchronizations and barriers between the CPUs and the GPUs so that no stale data can be read. So what I mean is, let's say CPU captured buffer 1, buffer 2, buffer 3, but GPU was still inferring buffer 1, right? Now, but CPU has already captured buffer 2 and buffer 3. Now, let's say GPU has finished inferring the buffer 1. At that time, if CPU is capturing buffer 4, the GPU might read buffer 4. So the GPU lost inferring the buffer 2 and buffer 3, right? So just ensure that, those mechanisms are taken, because not even a single buffer has to be missed. Otherwise, the GPU can give you a wrong inference, right? So that's pretty much about this. And maybe when it comes to the isolation, yeah, the hardware interaction. So you ignore the error code counters, you ignore the TRR, you just ignore it, and if at all you don't take care of that, the hardware can behave, in a very weird way, and, end of the day, again, your inference might be wrong. So I'm just taking inference as just one example over here, but there are a lot of things which can, go haywire. Yeah, let's go to this. So AMD. So I think early in 2024, there was basically a security bug. AMD had deployed their GPUs, and just a second. Yeah, so AMD disclosed a local memory leak vulnerability. It's basically called leftovers. So there was something called kernel invocations. So between the kernel invocations, when the second kernel was invoked, the previous kernel did not clear the memory, because of which the next kernel was able to read the previous kernel's memory. Now what happened is, that's the reason they call it as leftover locals. The first the first kernel left over some memory which was read by the second kernel, and that is not acceptable in the real world, because in software aspect of it, you can just imagine like you have two different processes, right? You cannot let two different processes go and read each other's memory because you're just leaking the data, right? So that is not allowed. So that was something found out on one of the AMD GPUs, but later, I think in May 2024, they released the driver updates, offering an mode to clear the memory of the previous kernel. Something very similar, I think this is with Tesla, but I think Tesla was using NVIDIA GPU, and there was basically a bug where the driver failed to properly clear and manage the shared memory between CPU and GPU. Again, I said shared memory between CPU and GPU, so that is where the bug was. But later it was fixed, like, they released the driver updates, and the kernel memory leftovers creating a serious information disclosure vulnerability. Sorry, I'm not moving it over here. Yeah, sorry, this was the Tesla GPU driver bug that I was talking about. Very important thing. Why hardware bugs are security bugs? I think I would like to focus on the third point. You might have firewalls, TLS, and permissions. They don't protect you if at all you have not taken care about the cache invalidations or memory management unit at the DRAM level or at the hardware level, right? So a hardware bug can break any of the integrity, confidentiality, or the availability, which is basically have combined together, and I'm saying it as security. Cross-layer amplification, a single hardware bug can propagate to the OS, the driver, and the application, corrupting or leaking the data across the test boundaries. This is important. So here, what is the best way to ensure that you do not lose any of these hardware bugs? From stage one, what is the best way to do it? Along with the software testing, I would say, while you're at the requirement stage, understand end of the day where your software is going to be deployed. Get some brainstorming or knowledge about what the hardware looks like. Now, come up with what can be the threat models from the hardware perspective level, right? So end of the day where your code is going to run, right? You know which hardware, from which company you're going to buy the hardware, and on which GPUs your software or the AI model is going to run. So do some analysis about the threat models, right? Put it in the requirement phase, and in the design phase, you take these threat models and you write test cases so that you can, end of the day, run your test which can test these hardware threat models. Deployment, again, secure code at all layers. Then testing, you do a lot of, the fault injection, the fuzzing, and end of the day, deployment with the telemetry hooks and continuous monitoring. Just don't monitor your software, even monitor your hardware. I'll probably pick all of those. Maybe important thing would be, let's talk about the application integration, right? The traditional approach was, yes, you always assumed APIs are safe, and someone spoke about, how to ensure API. You integrate the security when it comes to every API level. You verify the API inputs and outputs for boundary, right? But tooling, API input sanity hooks. When it comes to the cross-layer verification, test each layer in isolation. That was a traditional approach. You isolate and test it in every layer. But what you need to do not isolate while testing. Put everything together and do a rigorous testing. Just to give a quick background, so usually in industry what we do is, let's say you have a hardware, right? It comes back from the fab. So you do a very basic testing even without flashing the operating system on that. So that's called a bare metal testing. So hardware people, they run some the instructions based on which company CPU they're using, right? And they run the GPU ops. We do a lot of bare metal testing just to ensure that the hardware is perfect. Once you ensure the hardware is perfect, you flash the operating system on top of that. The moment you flash the operating system, people come up and start writing some kernel level programming. You also flash the drivers, so driver level programming. And then on top of that, you write your software code, and we call it software testing. So the software testing talks to the operating system, which can talk to the hardware. Now, once your software testing is done, then you bring in your AI model. So we do it from the scratch. So that's something I'm saying, that when it comes to the cross-layer verification, do not isolate it, do it stage by stage, and then integrate everything together. Okay, so we'll talk about the cross-layer security testing strategies. So fault injection, simulate row hammers, tail buffer, cache coherency faults, cross-device fuzzing, randomize the API, the DMA access to stress the every layer. Race conditions, I know race conditions, you do a lot of in multi-threaded programming, you write test cases for race conditions, but even in hardware also we take care of that. Security telemetry verification, again the ECC, the row refresh and the access violations. Now, I think this is something which is implemented by ARM recently. It is used by industries these days. It's called ARM MTE, memory tagging extension. So memory tagging extension is like this. So at a hardware layer, what we basically do is, so you have the CPU which is communicating to the GPUs. The CPU basically has to send the buffer to the GPU for inference, right? So you basically see a lock, which basically means that we lock it with some memory tags, and then we send it to the GPU. Now the GPU is going to validate, okay, is this the CPU the right agent to keep sending me the request? If the GPU feels that, okay, he's the right guy, then he's going to accept the request, otherwise he's going to ignore the request, right? So every transaction which basically goes is tagged with memory bits. So it is just not the data, we have the memory tags. So that's called MTE. So ARM MTE hardware enforces the tag match before any read or write. If CPU wants to write to the GPU memory, you tag it with some bits, and then let the other guy validate it. Only then it's the request will be accepted or the transactions will be accepted. So call to action for engineers: integrate low-level security in your code. I'm not talking again about the software security, but the hardware security. For architects, include the hardware threat models. That is the first thing during the requirement phase. The architects have to do it. Take that into consideration. Allocate the resources for cross-layer verification in every project. That's very important because hardware bugs are not like software bugs. Let's say you had a software bug. Let's say you wrote some unit test cases like C++. You wrote some unit test cases. You figure out, okay, there is a bug in my code. You fix it, right? But in hardware, it's not like that. So hardware is already fabricated. You have the hardware. But yeah, we still have workarounds, from the device drivers who can just go right into the system registers and they can fix the behavior of the hardware. But in most of the cases, you cannot fix it. So if you cannot fix a bug in a hardware, you will have to redesign it or give us fix to it, and then again you will have to send to the fabrication. They'll have to fabricate the hardware and send it back, because that's a lot of money, right? So we cannot lose that when it comes to the hardware perspective. So hardware verification is always much, much, much difficult when it comes to the software verification. So for others, it's just that shift from trust without verification to secure by design. I just wanted, the one key takeaway is never just think about from the software perspective, also think about from the hardware perspective. That is because your models are running on powerful GPUs, and GPUs are hardware, right? So yeah, I think that's pretty much I had for the day. Thank you.